Hello, so today we are going to do this problem, which is part of Leetcode Daily Challenge, Unique Binary Search Trees, number 2. So basically we have an integer n, and we want to return all the structurally unique BSTs. So basically it means BSTs that are unique, where when you have a node, the left child and the right child, basically for all the left and right child, there is at least one that is different. So you get the idea, it's basically just unique. And here BST is basically when the left side has to be smaller than the node and the right side has to be bigger. You can't have, for example, you can't have 0 here because it's smaller. You can't have 4 here because then it's bigger but it's to the left. Okay, and the nodes labels or values are from 1 to n, and we get n, and the goal is to return the actual BSTs, the actual all possible BSTs that we can get out of these nodes, out of these n nodes, right? So for example here, if we take n equal to 3, then we can do 1, 3 to the right, and then 2 to the left. And this is BST because 3 is bigger, so it's to the right, and 2 is smaller than 3, so it's to the left. But also for 1 element, 2 is bigger, that's why it's to the right. You can't put 0 here, even though it's smaller than 3, because all the children to the right have to be bigger than 1, okay? And for example here, we put 1, 2 to the right, it's bigger, so this is valid, and 3 to the right, it's bigger, so it's valid. And you get the idea for the rest. And the bounds here are pretty small, it's just only up to 8, okay? So how can we do this? Okay, so let's see how we can do this. So for example, here we have n equal to 3, and these are the possible ones, but how do we do it? So if we take this, what are the elements? We have 1 to n, so we have 1, 2, 3, okay? So intuitively, the BST property is that for a node, let's say root, let's call it root, or let's call it x, okay? Then elements smaller than x have to be to the left. So left means smaller than x, and right means bigger than x, the elements that are bigger than x. Here we don't have equal values because it's 1 to n, but if you had some, most of the time it's on the right side. And so here, since we want all the variants, and you can already see it in this solution for the first example, each value from 1 to n can be the root. So for example, first we have 1 that is the root in these cases, then we have 2 that is the root in this case, and then we have 3 that is the root in this case, in this case. And so each value can be the root, and then we can just see what are the possibilities for the left and right side. That makes sense. And so here we definitely know that, let's try first with 1 as the root. So if 1 is the root, then we can only have a right child. We can't have a left child because there is nothing smaller than 1. So we have to only construct out of this one, and then out of this one we can do it recursively. We can do the same thing. We can try to pick 2 as the root. Then in that case we only have 3 as a possible right child. We can't have a left child. Or we can try 3 as the root here, then we only have a possibility for a left child. We can't have a right child, right? And so 2 things we notice here. One is that this is recursive. This can be a recursive solution. And then the other thing is that let's just try each of them to be the root and then keep going, and then recurse the same thing for the values. Okay, so since we said that it's recursive, we need to determine what are the parameters that we are going to give it. Well, so let's say when we took 1 as the root, what do we need to give the recursive function? Well, we need to give it the remaining values here. What are these? Well, it's just a range, right? Let's say, what if n was 5? Then we'd have 1, 2, 3, 4, 5, right? Then if we take 1 as the root, what do we need to give the recursive function? All of these. How do we represent all of these? Well, we can just say the start is equal to 2, and then the end is equal to 5. And then take the 5 as the end. And let the recursive function handle picking 2, trying to pick and then 3, and then trying to pick 4 as the root. Okay, that way we first have 1, and then we have the right child as 2. Now in that case, we would have to put 3, 4, 5 to the right, because we can't do anything. We can't put 3 to the left. And and then we continue recursing for 2. So we then decide to maybe put 4 as the root, right? And so in that case, 3 becomes here and 5 becomes here. And then maybe we decide in the recursive function to put 5 as the root. Can we do that? So if we put 5 as the root, then both 4 has to be on the left side and 3 has to be on the left side. Okay, so this is sort of how we can do it. And then the other possibility is to put 3 here and put 4 here. And so you can see how recursive this is. For each function, it does the same thing. It tries to pick a root and then tries to construct the left and right child. Okay, so that's pretty much most of what we need. Then we just need to find what are our base cases. Okay, so with a recursive function where we give here the start and the end, then what are the base cases? Well, the base case is when we are done, like when we keep, let's say here, when we keep recursing until we reach 5, for example, or just 4. So the start is 4 and the end is 4. Well, in that case, we just need to return one node, which is the node 4, with nil left and nil right. Same thing if we are just start equal to 5 and end equal to 5. So one base case is definitely when start is equal to end. In that case, we can just return a tree node of the value itself. So start, since they are equal, you could use start or end. The other case is what if they cross each other? Like we have, let's say, maybe start, we keep going, and start and end. Maybe start, let's say, is 5 and this is 4. Well, in this case, we should just return nil, because this means we got called on a recursive function for a single node. And so in that case, we can just return none, so that whatever child is to the left or right should be none. Okay, and that's pretty much it. Those are the main ideas we need. Of course, when we do the recursive function, remember for let's say for 1, for example, here, if we take, for example, this 2, actually maybe it's easier for 3. If we take 3 as the root, then we know the left child are all the combinations that we can construct from the left and all the combinations that we can construct from the right, because if we take 3 as the root, then we can have 2 here and 1 here, and then the other possibility is to have, and then we have the right subtree with 4 and 5, and then we can have 1 here and 2 to its right. Okay, this is also valid, and then the right side with 4 and 5. So you can see for each recursive call, we will have a list of subtrees, and this tree we need to create a new tree for each of these combinations. Okay, and similarly, we have to do that for the right side. So that's something to keep in mind when you are doing your recursive function. So you will probably need to do a for loop for each left list of trees, and then another nested for all of the ones on the right side. Okay, just so that you can do a combinations for all of them. Yeah, so I think with this we can start writing our code. So let's jump into it. Okay, so we need definitely a recursive function here that we said needs to have both, let's call it trees, because it gives us the subtrees, or all the trees we can construct. And we said the recursive function parameters are start and end. And now we want to check if start is equal to end, which is our base case. Then we want to just return a tree node, right, of the value start, right? Now, why do we have a list here? Remember what I said earlier, because for each node, let's say 1, 2, 3, 4, 5, here, when we are, for example, considering 3 as the root, for this one, we need to attach to the left all the combinations of the left side. And so here we have to return a list so that we can loop. And that will be clear later on, but I want to mention this still. Now here, start bigger than end. We want to return when it's not none list. Why none here? Same reason as here. You'll see it later, but if we return just an empty list, right, then we'll get nothing to attach as a left child, and so we won't loop, because remember we do for L in left and for right in the right side. So if we return just an empty list, this won't loop. So if, let's say, for example, in the case of 1 here, it doesn't have a left child, but it does have right children. So it does have right subtree. So if we don't return none here and return just an empty list, then this loop won't execute. And so we won't attach any right node, which would be wrong. Okay, and so here we have to return none so that this loop executes. And for example, node 1, we are going to attach a right child. Let's say, for example, right is going to be a subtree that has 2 as the root. Okay, and then of course the left child is going to be none. Okay, but if we return just an empty list, this won't happen. Okay, so that would be bad because we won't solve for the case where 1 is the root. Okay, and now we can just do for all the, so basically we try each node, each value in start to end as the root. Okay, so that's what we do here. So let's call it maybe root in the range of start to end. Now we need to do end plus 1 here just because of Python, so that you can go all the way to end. You have to do plus 1. Now we can try, we generate the left side and the right side. So we can just recursively call for the left side and for the right side. Okay. Now what would be the parameters here? Now the left side, let's say for example 3 here, we said the left side is going to be everything to the left. So basically it's, let's say this is the root, then it's the root minus 1, right? So let's actually maybe call this x. So this will start from the initial start here. Okay, and then from the start to r minus 1, that's what we need for the left side. So here it's going to be start to x minus 1, and for the right side it's right after x, so x plus 1, which is 4, all the way to the end. So here, even if you had other values, it would be the same thing. Okay, and so here it's going to be x plus 1, right? And the last element is going to be end, right? Okay, so now that we have these, we need to do what we said here. We need to go through each combination, each possible subtree. And so what would be the node? Well, the node is now it's very clear because the root, we know it's x, right? And then the left child is going to be the left subtree here, and then the right child is going to be the right subtree. Now we need to add this to a list of results so that we can return it at the end, right? So that, for example, when we are doing 3 and we go to 4, we do get all the subtrees of 4 and then add them to a result and then return them to 3 so that 3 can attach them to its right. Okay, and so that's what we do here. So res append this node here, and now we just return that result. Now that we have our recursive function, we of course need to call it. So what are the start and end? Well, we already know that the nodes are from 1 to n, so that's what we need to have here. And so let's run this and let's submit it, and it passes. Okay, now one thing I want to mention here is that we actually don't need this, so we can sorry, not this, but we don't need this because this basically, when start is equal to end, x would be equal to start value here, and these two will return none, and so we'll just create a node with just the value of start, and so that's the same thing as here, so we can just get rid of it. We can submit, and that passes still. Now another optimization even which we can do, not really a big deal, but we can just remove this, and if the list is empty here, which means we didn't get any values, then we can just return a list with none, so that this loop and this loop always execute. Okay, so that we don't, if a node has only left children or has only right children, we still attach them. Okay, so let's run this again, and that looks good still. Now here the constraints are really small, it's only up to 8, but if the constraint were bigger, then we can cache, because there are repetitions. Even if we just print here, we will see that if you just print here the start and an end for your recursive function, you will see that sometimes especially for bigger values, start and end would be called the function would be called with the same start and end multiple times. And so to cache, you can use either a hash map, or in Python, we can just use this cache here, and this still works. Okay, so this basically will cache using the keys start and end. And the value would be basically the list of trees. Yeah, so I think that's pretty much it for this problem. Please like and subscribe, and see you on the next one. Bye.